Okay,
Yes.
thank you very much, Yancy, for the invitation and for the chance to participate here. I'm going to talk about, in fact, the S in the STEM that we've just been talking about, and in particular, in fact, even half of it, because I'm going to concentrate on chemistry, although I'm sure it could be relevant at least to physics and to some of the other subjects as well. So I want to talk about practical work in particular and its alternatives, and how this enhances our teaching of problem-solving skills and also students' readiness for tertiary studies. Now, I think we all know we've had so much research on students and their problems with problem solving. We know that we need to jack up the teaching approaches, the methodologies. And I think part of the problem may be that they don't do enough practical work. If I can just briefly explain Johnson's triangle of the dimensions of chemistry. So we have the macroscopic or observable dimension, which is what things actually look like, things that you can hold and observe. Then the submicroscopic, which is the particles that make up that substance, and then the symbolic, which is how do we write it in terms of chemical symbols and so on. So I've got calcium carbonate as an example here. So calcium carbonate is actually chalk, it could be or marble, and it consists of these particles. Now, practical work concentrates more on the macroscopic, the tangible, the observable part of chemistry. And without it, many teachers concentrate on the microscopic or the symbolic aspects. And sometimes chemistry becomes very abstract, and then there can be misconceptions. So, for example, if students are given an equation and asked to balance it, yes, they can do it. I found students who are quite competent, they can balance this equation. But I go into the lab, I give them some copper sulfate and some copper, and they cannot tell me which is the metal, which is the salt, because they do not know what they look like. And this is because they've never seen them, they've never had to touch them before. Now, if we look at South Africa, we have the National Subject Diagnostic Report, which we get every year after the grade 12 final exams. In physical sciences, I've gone from 2019 to 2023, the pass percentages, but remember a pass is 30%. So the achievement range from 62 to 76%, which you might say is reasonably good. If we look at 40% achievement, the percentage of students who pass is down to 40 to 50%. And if we go to 50% and above, which is what we need if the students are going to come to university to do a BSc, we find that only about 30% of learners actually achieve that. If we look at the CAPS document, they've got the syllabus. I've got here grade 10 and 11 and 12. There's matter materials, chemical change, chemical systems. It's good. What is taught is actually very good. But if we look at the bottom, the skills for practical investigations, 2 practical activities for formal assessment. We can forget about the recommended ones because I think a lot of schools don't do them. They don't even do those 2 prescribed practical activities. And I think this is part of the problem. So I'm going to talk now a bit about a study that was done at Northwest University. And this was part of an MSc dissertation done by my MSc student, Kelly Branches, who I think is online at the moment. He has submitted it, so it's still under examination. But what he did was he developed a questionnaire to test the understanding of stoichiometric concepts and attitudes to practical work of first-year extended and mainstream BSc chemistry students. This was in our faculty at NWU at the Mafikeng Campus. And he also interviewed the lecturers and the lab technicians who were involved in teaching these modules. We had 338 students who participated. which was a 60% sample of the entire classes. So that was quite a good sample because, of course, it was entirely voluntary. Now, if we look at some of the concepts that were tested, the first one there, to recognize a balanced equation. So they were given various equations and had to say which is correctly balanced. Yes, they could do that. If we go a little bit lower down, take an unbalanced equation and balance it. Yes, most of them got that right as well. But the one down there in yellow, writing a balanced equation when all they were given was the reactants and just the names of them, not even the formulae, suddenly only 8% could do that. And you can see they also struggled a lot with acid-base titrations, preparation of standard solution, and working out excess reagents. And I think part of the problem is that they had never done this. So then when the staff were interviewed, a couple of the things that they brought out in terms of their laboratory practice was they hadn't been into a lab before. They didn't know what was a pipette and a burette, for example. They hadn't used them. And then they struggled to read the burette, for example. So they'd say the total volume, and we know you take final minus initial and so on. They would come out with a negative volume. They would then use that and do their calculation of the concentration of a solution, and it would be negative. And they wrote it down, and they didn't seem to think, but that cannot be. What have I done wrong? We also found there were lots of breakages because students didn't know how to handle the apparatus correctly. And then some of them have not used a computer before. So when they were asked now to write up their reports, to type them, they were not able to do so. When they were asked how many practicals they had actually done at school, nearly 50% of the students said they hadn't done any practicals at all. If you look at some of those practicals that were meant to be done, titration I know is one of them, and only 35% had done that. And then practicals on a standard solution and on a limiting reagent, only about 20% of students had actually done that. I may just mention that these students also gave the quintile of school, or the name of their school from which we could work out the quintile. And they came from all quintiles, from 1 to 5, and there were a few from private schools as well. So they weren't all from disadvantaged backgrounds by any means. On the other hand, when they were asked how many of them had watched demonstrations, it was not very many. How many had watched videos? It was less than 50%. Simulations, hardly any of them had used. 62% of them said their school did have a laboratory, but only 36% said that they actually had all the equipment that they needed to do the practical work. And again, even though half of them said they did have a computer lab, only about a third had access to Wi-Fi. And then they were asked about their perception, how satisfied they were. This was on a Likert scale of 1 to 5. So the number of practical activities done, the average answer was 1.8, which you can see they were not really at all satisfied with how much practical they had done. And also the alternative practical teaching methods they were not satisfied with, although they were a bit more satisfied with how the practical concepts were taught when they did do practicals, and the teaching methodologies generally, they were reasonably happy with. Again, on their perception of practical work, they definitely did not agree that practical work was not important. They again did say that it did improve their problem-solving skills, and they were definitely not bored or unnecessary. So they were very positive towards that, and quite positive to say that it did help them to understand, and definitely practical work must be increased. 4.5 out of 5 is a very strong score there, and that they were quite easy for them to understand. So there's been quite a lot of research looking at the achievement of students who have done practical work, and generally the conclusion is that it's better if they do hands-on practical activities. But now the problem is that, as we all know, a lot of schools do have very limited resources available. And so what I want to do now is just discuss a few of the alternative methods to hands-on practical, such as demonstrations, hands-on practical using microscale and small-scale practical activities, and then simulations and virtual laboratories. Some of what follows, I'm going to draw on papers presented at the 27th International Conference on Chemical Education, which has just taken place in Thailand in July. So there is got a couple of pictures of the conference. Of course, I was there. Here is the chairperson of the ICCE, Super One from Thailand, and then the chair of the IUPAC Committee on Chemical Education is our very own Mariki Potgieter, who we might know. She has been at University of Pretoria. So South Africa was represented by a few people. It looks as though women were also very well represented there. So the hands-on practical traditionally has been the gold standard for chemistry. This is what we must all aim for. So what we expect, or what we hope for, is a group of students. You can see they're all wearing their correct PPE here. They are all engaged. They are working. They are learning very well. That's what we all aim for. In COVID, our lab looked a bit more like this. To begin with, of course, there were no practicals at all. We weren't allowed in the lab. When they did come back in 2021, we still had to have a lot of isolation. So instead of a class of 200, we had very few students in the lab at a time. And now imagine how difficult that is when you've got 200 students and you can get, say, 20 in the lab. It made it extremely difficult. The advantages of hands-on practicals, as we know, the students can manipulate the objects themselves. They learn through all their senses. And the more progressive types of teaching, so inquiry-based learning, student-centered learning, are very easy using hands-on practicals. On the other hand, you know, it does take time to organize a good practical lesson. It's expensive. We need the laboratories. We need the equipment. When we have large classes, it can get a bit chaotic. I've been in a lab that should have taken 100 students, but there were 200 in it, for example. Safety aspects are then quite a concern. And even though they are doing the work themselves, it's possible that they follow the recipe without really understanding what they're doing. So the alternative to practical work that has been most widely used is demonstrations by the teacher. Again, we expect a teacher with a small group of students who are engaged, who are asking questions, who are all able to see the demonstration very well. And that also isn't always the case. Sometimes, the students see the experiment and you only need one set of apparatus and chemicals instead of one per student, so it's a lot cheaper. The teacher can control the safety aspects and can explain the chemistry during the demonstration, so the teacher can make sure that learning is taking place. However, you still do need that full set of apparatus and chemicals. The students don't use it themselves. The problem, again, with big classes and big venues is that you get a few students at the front who are engaged, and then you might get a whole lot at the back who are just sitting chatting because they can't really see it. And the lesson becomes rather teacher-centered. It doesn't generally lend itself to inquiry-based learning. Now, one of the interesting papers at the conference was on demonstrations using small scale and micro scale. And I'd like to just refer people to David Katz. I've got his website up here. It is freely available, and he is more than happy for anyone to log on and use all of his resources. He gave it out at the conference and would be very happy to see people using it. He also gave very good papers. So the previous ICCE was actually here in Cape Town in South Africa. And there are very useful resources on his website that people could use. So, for example, he talks about chemical demonstrations, the good, the bad, and the ugly, and he talks about some of the things that should be avoided. And there is David giving his paper at the conference. So I think it would be quite useful if anyone would like to, just to go to his website and to see what they can find that they can use. And then microscale kits can also reduce vastly the amount of chemicals and apparatus that is needed. It can be a lot more inexpensive, a lot easier to get into the schools. So that's an example of a microscale kit. And here is another one. I know at Wits, microscale chemistry kits were developed. And in fact, what our university, which is now Northwest, we were UNIBO in the 1990s. So we had a kit like this developed by Somerset as well. And now you need a fraction of the chemicals that you needed before. And then another one called MyLab, and this was developed by Marie Dutoy, also at NWU. So we've got pictures of her at the conference doing a workshop using her apparatus. It is small scale rather than micro scale. And the advantages here, it's actually a bit easier, I think, to manipulate to see what you're doing because it's not so tiny. So her kit contained everything that you might need. So there is just a picture of her kit. It was designed around a 5 milliliter test tube. So it's not that tiny little micro scale that is possibly less than 1 milliliter. These kits could go into the schools and all of the practicals that are prescribed in the CAPS curriculum can be done using these kits. It contains everything. The only thing that they need is a bottle of water and a roll of paper towels. Otherwise, everything is there. You don't need a laboratory, and the learner and teacher manuals and the DVDs are also included. Another interesting paper was on distance learning and experimental chemistry, and here we have Jorge Ibanez. And he actually went into his kitchen and designed and assembled his own microscale chemistry kit and distributed it to the students' homes. The advantage was he had about 20 students and they all lived reasonably close by, so he could do this. But it was for electrochemistry and corrosion practical, so it was a high level of chemistry. So we're not only talking basic education that can use the microscale kits, but even at a much higher level, they can still be used very effectively. In fact, he even had students designing their own experiments using these kits. The advantages of this, of course, is now it's a lot lower cost because you are using a lot less. So safety would be increased. It is environmentally friendly. There will be much less waste. And these kits can be used anywhere. If you've got a laboratory, great. If you want to use it in a normal classroom, you can. The students can use them at home and they can do them in their own time. And during COVID, of course, they could be delivered to the students' homes. The microscale, I find, can be difficult to manipulate. Maybe you disagree with me and think that it's perfectly easy. And then there are simulations, such as the PhET simulations. Again, these are totally free to use. I've got the website there, and everyone is welcome to go to the website, download them, use them. Students are able to manipulate objects on the screen themselves, and so it is a lot more interactive than, for example, some of the things like just watching something on screen. So they are able to manipulate them. They can have a sort of game-like environment. Of course, there are far less safety concerns because they're not using real objects. It's ideal for self-learning. It is free. You do, of course, still need the internet and a computer, and the objects are not actually real. But we can get past that problem of needing the internet by using digital offline. And at this this precise webinar that took place 2 years ago in 2022, there was a fascinating talk by Dr. Derek Fish talking about doing digital offline. And what he did was he took his simulations and his applications, loaded them onto a memory stick, so that the students could then use them. Okay, they needed a device, but they did not need the internet. And the link there is just to the NSTF website, to the presentation that he actually made there. So with these, experiments always work. I mean, I think we probably all know we've been in the lab doing experiments and we try and do a demonstration and then say, oh, it didn't work. These ones do. There would be no connectivity issues, no ongoing data costs. Again, the videos can be watched anytime. They can be paused and replayed as many times as the students like. You do still need a device. Those videos still need to be made and the memory sticks need to be bought and distributed. And the problem with being on an offline environment is that if things become outdated and need to be upgraded, you actually have to remake those memory sticks. And then virtual or augmented laboratories. The virtual reality software was originally developed for the gaming industry, but it can be used very effectively in chemistry teaching. It can teach both macroscopic and microscopic concepts, and you can get these amazing immersive systems with a head-mounted display. You've got real-time motion, you've got a wide field of view, you've got high resolution, you've got stereo sound, and a large number of articles are being published on the subject. I've just included a few of them in here. So this looks like a virtual shot of a virtual laboratory, but the students can have headsets on, they can manipulate objects on screen, and they can have the microscopic representations there in their field of view as well. So there were a lot of papers on this at the ICCE. I'm afraid I'm not an expert in it, but it is an ever-expanding field that we could also look at. There are some of the presentations. I've just included some here. I know you can't actually look through them all, but I've highlighted they came from China, Germany, Turkey, Singapore, and then there are more: Thailand, Singapore, Thailand, Australia, Hong Kong. It does look a bit as though the Asian countries are ahead in this game, although actually, because that is the location of the conference, that could be why it was skewed in their favor. But it is a very fast expanding field, and that has a lot of potential for use. So the advantages and disadvantages are much the same as simulations. Really, they're just more advanced technology than the initial simulations. They are flexible. The students can get instant feedback. Technology is advancing fast. It's becoming more and more sophisticated. And these Gen Z students that we've got now, I think this really appeals to them, and they are very adept at using these things. It can be used to teach all three of those levels that I talked about, and it is quite possible that they do enhance understanding of chemistry. All right, so just a few recommendations before I finish. First of all, as I think we all know, the Department of Education does need to increase the availability of resources at schools. Ideally, every school should have a practical laboratory that is well equipped, and more formal practicals should be given to students on a yearly basis. I think it's a challenge first to get those practicals into the syllabus and then actually into the classroom or into the lab. Then what do we do if laboratories and equipment are not available in schools? It doesn't mean that teachers have to sit back and fold their arms and say, well, there's nothing we can do. In fact, I seem to remember once a student telling me, no, they couldn't do a practical in their class because there was no sodium chloride. And I said to them, well, why did you not go and just bring in a bottle of salt? It's not an excuse for not doing practicals. So there are alternatives that can be used. So microscale and small scale kits can be rolled out to schools at a much lower cost than traditional equipment. And then virtual laboratories can also effectively enhance understanding. And I think in future, possibly the best would be to use a combination of both virtual and hands-on activities to enhance learning. It's really important that students are exposed to enough lab exercises before they enter university. Otherwise, what we find is when they come to university, we're playing catch up by having to teach them the skills in first year that they actually should have got at school. Okay, I've used quite a few references, and I've also just listed all those websites that I had during the talk. So thank you very much.